All right, we're going to use Python to do some analysis of semiconductor metrology information we took in the MPL. Um, I'll just roughly go through the code and what's going on. So first we're going to import Pandas, and that's a database tool, but it's short for panel data, which is descriptives, which is mean, average. You'll see it later, but it's so much more, right? We're going to use the scientific calculation package from Python Numpy, and we're going to be plotting things. So I have 3 lines here, and I have some variables equaling to some very long strings. And these are the sheets, the specific sheets to the data we're interested in. So if we come over here, we have the 4-point probe data, the nanospec data, filmetrics data, and every column is a variable, P1, P2, P3. That way we have to all keep it the same, right? In this case, we had operators, but you can see that it's not in any particular order, right? You can see the naming convention so that I can find it. But if I want to share that data into Colab, you publish to the web, right? And this is nothing secret, so I don't restrict the access. And anytime you make a change, eventually it'll show up when you run the code. But I don't want the entire document. I want the 4-point probe. I don't want it as a web page. I want it comma separated. And I just can cut and paste that link into here. And I just repeated it for the nanospec and the filmetrics. Now, yeah, somewhere we know that that's just the voltage current relationship. It's not actual sheet resistance. I calculate that later. So I take some data and I read it in using Pandas CSV read tool. There's other ways to do it. You don't have to use Pandas. Pandas, I use it for a lot of the, let's call it my social science type research. But there's other ways to do it. But then we turn it into a database by, we read in the data, then that's just make a data frame, right? And then here, I'm making a list of the variables across here. If I recall, don't have any spaces, keep it simple, no special characters, because then it can be hard to access later. So I want to print out the descriptive statistics for each column, right? So for column in data columns, right? So the series equals that. And so it's one of those Python things. It'll just automatically pick up the word run, operator, P1, P2, P3 as it goes through, right? I print out a, I don't know, space. And here are the descriptives, format, variables. Oh, maybe that's, just let me, I had deleted some code like, I said, why am I got that variable there? Anyway, so now, and this is, now we're kind of going to analyze it, right? And like, does it make sense, right? Do I have to be able to trust you all? You have to be able to trust me. So the count, right? We had 14 people there that day. There should be 14 measurements. And the first column was just run. So 1 to 14. So yeah, what is the average of, 1 plus 2? you know, what is the average of the data in that column, right? So it should be straightforward. Yeah, it calculates the standard deviation just because, right? What is the smallest value? 1. What is it at 25, 50, 70? What is the biggest value? Okay. Then we get into the descriptors of the variable operator. Well, notice it has count and it has unique values, and it just says top, Jennifer. And I believe that's because you're the first one there, right? Um, and then frequency, how many times did you show up? Once, you did one data. But then nothing else is there because it makes no sense. Now you could probably convert the text to ASCII, then to numbers or whatever, but notice it just, and so I don't want to mess with the data set, but if I put in like a character in here, it would just skip over it and it would throw off, you know, things. But that makes sense. All right. So for P1, 14, what is the mean? 0.009, standard deviation, min, max. Okay. So you can start looking like, all right, for point 1, the mean is 0.09. But then for position 2, it's actually seems higher. Now, yeah, the standard deviation can kind of tell you whether it's meaningful. Here, the standard deviation is smaller than compared to position 2, right? Um, so again, you know, we don't, I'm just using this to see if the data makes sense, right? Because if I saw 3,000, I'm like, oh, somebody put in an oxide thickness in the or typed it in, right? So, you know, that wafer, which I don't even know how the aluminum was put on it, right? It was just something kicking around. Yeah, it just might be, right? Having a different means. Because sometimes it's 0.06, 0.19. All right. So now I do a lot of things. I'll spend a lot of time to make it so that I do not have to do things time and time again. So you can use a graphical plotter like, you know, people like Excel or Google Sheets, but you got to fiddle with it every time. Here, once it's programmed, then I can go and get it set up and it runs every time. And the thing is some of the way I programmed it is that if actually, Tracy, if you had 10 points, right, and the first two things you wanted to ignore, it would find them all and it will plot it all automatically. You wouldn't even have to change it, right? So because I stripped out the run, I need to make a variable for, instead of plotting by operator, it's just going to be 1, 2, 3, right? So X NP arrange from 0 to the length of the new database columns, right? So I got rid of these two. So what is the length of the number of columns? So see, I'm already, rather than say 5, right, and hard code everything, no, length. So I in range of this. So that I is now an integer, right? And now this is a little trickier in Python. So what is the data in the column? Convert it to a Numpy array from Pandas. And this means ignore the row and then just go after the column. And then here, I multiply it by the value to turn it into sheet resistance. Now, as soon as I typed in times np.pi divided by, it popped out divide by np log 2. Like it knew somehow. Today, it was actually providing good hints for code. Usually I have to turn it off because it's really annoying. Then we have plot the data, right? So X, that's our 0 to 13. That's the data column in question because I'm cycling through. That means make a circle. And then here, I want to have it a label, right? But I won't want to have to do label P1, P2, P3. So I have label, and this is kind of like a placeholder, and then I use the command format variables.i. So I cycles through here, and it's this kind of neat Python trick where then it'll just take that num P1 and just put it in there automatically. And then here, what is the run? Units, unitless. Sheet resistance, ohms per square, which it took me a long time to find that darn box. And then the box had a dot in it. And I could have figured it out, and you install LaTeX on the fly. I'm like, you know, I'm going to live with a dot in that box, which is major flexibility on my part. But you guys were coming at 9. So anyway, now we can see our data, right? And we can see P1, right? Which one's that? Blue-ish? Oh, yeah. Let's see. There's purple is P5. Okay, so P1, right, is kind of right near, it's somewhat hidden. It's either hidden behind P5 or hidden behind, yeah, or what's orange? P2, right? But it's there, right? But you can see the reds are kind of following, the greens are about the same. The orange looks pretty good, but we have this data point up there. It's pretty high, right? That is looking like something happened. And then we have purple, okay? So now that's the thing. I don't think, so let's see. It's just going to be the biggest number here. What was it? Orange is P2. So it's like P2. And so we can see this big number. Now, yeah, I'm looking at it. Everybody else is 0.0. That could be 0.09, right? Because that's what so I could just make a command decision and like, well, I think that was a bad data point entered in like a typo, right? I'm going to leave it there because, no, yeah, I probably should have masked the names because now you can tell whose it was. But I mean, let's just say it's a bit philosophical. Is it real? Is it, because now we're getting into cherry picking data, right? And which is a major sin of, well, let's see. No, she made up data. There was a Harvard researcher on honesty. I don't know if you read about it. And they published a paper that if you signed an honesty pledge at the beginning of a survey, you would be more honest in your answers than at the end. Well, it turns out they put in a lot of fake data. So, yeah, ironically, and yeah, they've been like the only person ever to be fired from Harvard, right? Now, the thing is if I'm like for social science, if I have a theory, right, and this person is, let's call it a person now, right? And like, well, that's not really satisfying my theory. Hey, that's a bad data point. Let me get rid of it. But wait, is that a real data point? Well, so the thing is some people are, no, everything has to stay. But on the other hand, that might not be true. I don't know. Have you guys done Scantrons? Okay. Well, some people like to play jokes, right? And you can look at the Scantron and like they're just kind of doing stuff. Well, um, sometimes they'll ask more than one question on the same thing to see, well, these should track. And if it's not, maybe. So you can say, well, this person, we're going to get rid of that survey because they were obviously fooling around. But you have the original data set and you describe how you got rid of it. So if I were doing kind of a detailed analysis and I would show this and then say that data point, looking at all the other data points and the fact that it's hand entered, right? Just like the nanos, yeah, sorry. But, or, you know what, I probably entered it, I fixed it. I ruined your data to make a point. That's probably what happened. That's something I would do, is I just randomly made something like that. So I said, we have this data point, it looks like a typo. And so then we would change it, but our process would be buried in there. Now, yeah, that might just be in the lab notebook rather than the final paper to be published. You just say, here it is. And then, yeah, you could say, here is all my data and put it on GitHub. Come analyze it. Now, yeah, people like to keep their data secret because you can generate papers out of it. If you give your data away, anybody could do a paper. Where's my funding going to come from then? Anyway, so now it's just like, yeah, it's grouped, right? You can see that it's grouped and that there's probably a relationship with position. But, you know, I have a string of data on an axis. I want to know, is there a relationship? Because you think there's not, and then all of a sudden there is. I had Terry's project, I wanted a data set with no relationship. And it turned out there was one. Right? So, so now there's another package from Python, SciPy stats. And now I'm going through the same columns. I could calculate it once, but I guess I'm doing it again. But now there's the slope, intercept, and R-squared value, p-value, and standard error. So this linear regression, that is the x, that's the data in question, put into sheet resistance format. And the slope is just like y equals mx plus b. That's m, intercept is b, and R-squared is that least squared fit, right? P-value is whether you're significant or not. And then you'll see, like, for position I, 1, the slope is this. And it just cycles through. All right. So these are all position 0. Yeah, there could be, oh, where's the intercept? Oh. So this isn't formatted particularly nice, but for position 0, the slope, not the value, is 0.009. The intercept is 0.39. R-squared is 0.28. Now, to me, that's kind of low, right? If we were all measuring the same thing, it would be totally flat and it would be a perfectly straight line. And so R squared would be like 1. But we were choosing slightly different positions. And then the p-value, right, it's 0.32 or 32%. Well, that's bigger. I was about to say, that's a lot bigger than 5%. It doesn't matter. It's bigger than 5%. There's no relationship on position 1. Position 2, sorry, position I, everything starts at 0. Okay. So now, okay, position 1. Then the slope, it's about the same. The intercept is much different. R squared is even worse, and which is, I can say, right? And p-value, yeah, I've never seen a number that big. All right, position 3. The slope, range, intercept, R squared. R squared is a little bit higher, but still no relationship. Going through, p-value, 0.03. Says there's a relationship. Okay. But every other point didn't have a relationship, right? And then in position 5, we're kind of back. So again, position 2 had the lowest R squared value because of that point, right? And yeah, because because that's so high, it's not really zoomed in, so it is a little bit hard to tell, right? So now what I want to do is plot the line with the data. All right, so now I'm going to I'm going to repurpose the variable slope. And so we have 5 points, I want 5 slopes. So what I do is I initialize a matrix, the length of the number of new columns, and make it filled with zeros. And the same with the intercept. So now I have, otherwise you have to go through and append. Python likes it better when you tell it the size of an array. And so then we go through again. So before, we just calculated and printed out whatever. But now slope I, intercept I didn't care about these anymore, so I just left it. And I replot it. Great. So now everything is calculated. And now again, I have the data on that particular. But then here's my y on that particular column. It's the slope I plus the intercept I times x. So I plot out the data originally, and then I plot the line. Okay. And so you can see, now the colors seem to be, it keeps cycling the colors automatically, and I tried to put a stop to that, but I ran out of time. So you can see, like, yeah, here's this orange line that's probably going through the greens, and you can see how it's just not fitting because of that. But then even this, color Where is that? P1. What is that P1 doing so high up there? Anyway, let me come back. Oh, I guess it was there. All right, so it's a thing, right? But now you did a linear regression and you can visually see the data, right? Now, yeah, what would I say? I guess I didn't do is you could come back to the panel data, right? And just say each point has a mean and a standard deviation. And what would be like even that, like I don't, you can do everything in Python, but you know, how long will it take? So if you draw a wafer and just say, you know, mean, standard deviation, draw a picture and have those numbers there, right? Now you can kind of see, oh yeah, all right, this is thicker, this is thinner. But now, oh, and then, yeah, what I didn't do is what is the mean for everything for the wafer, right? But now, like if you gave this report to a TA, right, and they're about to go do the sheet resistance measurement, is like, yes, this is what you can expect. But like this would be my final thing, and I'd say, you know, there was no discernible operator difference, right? The standard deviations, though, were probably caused by slightly different spots, right? Now, probably would want to go, there could be like, how hard do you bring it down, right? That might be an operator thing. But, so yeah, thickness is this, or the sheet resistance is this is typical, right? And I know it was evaporated, right? I just don't know which machine. I have to, sometimes there's a clue, right? Um, but like my evaporator, that's the wafer, but the aluminum source is off to the side. So you're kind of, you know, it's like a flashlight. And so you could be kind of getting something like that, right? This other evaporator, you had wafers like this, not drawn to scale, and there's a wire coming in and out. And so, you know, it's all going like that, right? And then the sputter system is a whole other deal, okay? But what I want you guys to do is, yeah, make a copy, right? Because I probably gave you edit access to everything in the directory, right? But make a copy and then do the analysis for the other things. Now, in some ways, all I got to do is go URL nano. Oops. Right? How would I do that? Cut and paste. URL nano. And just run all. Now you might then want to have Python code one for this, one for that, because while it will run, okay, so now Eden, you're on top. The means are different, right? You can see that. We do have some odd points, which really seems like I'm like being a pain. But it's still run, but it's actually oxide thickness, right? Angstroms. But we've still got some points. Here's all the values. And then, yeah, this one is really far off. So that line is like that, right? So it probably comes out here. Descriptives for one. All right, the mean is 1400, 1437, 1431, 16, 16. All right, so let's just look at the data. That was nanospec, right? Well, there is a missing one. And then some rather thick values there. So what I would do is, I think we know what wafer it was, or we have to hunt it down, and we can just double check. But yeah, there's a missing point, which would then, you would see, it would come out like 14, 14, 14, 13, right? So yeah, there needs to be some work there. So this could look like, man, this is the worst thing ever, right? Let's see, who is in charge? Oh, Hannah was in charge of this one. However, look, it's between 640 and 780, right? And it looks somewhat random. Well, if I had an even film, that's actually what I'm going for. So let's just see. Slopes, R's. So, so 0.1, R squared is very low. The p-value not significant. Position 2, same deal. Position 3, R squared, yep. So there seems to be no relationship, right? So that's actually pretty good. And for the 4-point probe, I think is easier to get somewhere in the same spot. But with a nanospec, you can't even see the light. It's like all over the place, right? So there's no relationship, right? So yeah, looking at some points, it looks, yeah, you can't really tell. It's just random, right? Which, but it does have, from 640 to 740, for that process, that's all you can count on. Like, don't design your process to need 5 angstroms of accuracy. But let's just come through. So the mean, Uh, I for, I multiplied it by the sheet resistance. All right, so you're getting a huge, so anyway, so 146, 144, 140, 150, 157. That's pretty good, right? Now, yeah, it just makes it bigger. So instead of 100 angstroms, but see, like all those little things in there, and it took me a while to like, wait, because I forget what we were doing. So just let me. So that's why in the end, yeah, make your own, make 3 copies, right? So that, so yeah, you got to go through that and then do the analysis. I got to come up with like a simplified report format. Right? And then, since we're here, I should probably put 880. That was the process. Right? We'll make it easier to find. So we have this issue. Oh, I didn't analyze it? Oh, analyze the data. Script not ready. Oh, okay. Um, oh, well, yeah, we have the data from yesterday, right? The difference now, it would be the same thing. There'd be P1, P2 here, but this would actually be, um, that's why it needs a little bit more. There's 5 measurements per wafer. So yeah, you have a column of P1s, but they're not, you have wafer 1, P1, 2, 3, 4, 5, wafer 2, so you have to manipulate it, right? Which I've done somewhere else, but yeah, so we're not ready for that. But now you can do that one, and then when you turn in the report, you can, then I'll check you off on knowing that. And then just, what I want you to do as well is make a copy of your own, make a copy of the data, right? And then you can decide this data point is bad or this is good, or then we can, all right, so on your own, go find the wafer and find the right data, right? That way you don't want to edit this data set, right? Because of course this will, you'll be immortalized in a data science experiment as long as there's a San Jose State. Okay. Um, now, all right. So that's it for the recording.